Hello, my name is Ankan Vardhan, and today we'll start off with our project BER analysis of radio receiver equalization algorithm using BPSK signaling. So the overview of the project, we'll have an introduction of the project, how it works and what it does. We have the motivation of equalization, which is basically to mitigate inter-symbol interference, which is ISI. We have the equalization model, and we will show how an equalizer works. We'll have a small overview of the equalization classification, and we have different adaptive equalization algorithms. We'll straight away narrow down to two of the very famous equalization algorithms, which are zero forcing and MUC. We have few metric notation which are clearly mentioned in the slides later on, and which will be used in our mathematical modeling and notations. For our simulation, we have BPSK signal, which is also known as antipodal signal, and we'll pass it through the channel. The channel is modeled as EWG and relay fading. Now we will pass these through zero forcing and universal equalizer, but before that we'll pass it through EWGN and relay fading channel. We'll see the BER performance, and then we'll find out the ZF and MMSC implementation, and then again find the BER performance and compare it with the previous performance, and we'll check which equalization algorithm is better. Now we know the wireless channels are hostile, so we have to compensate for whatever impairment the channel does. So but basically how to go about that? By just inverting what the channel does. But how? We have to know how the channel behaves. We have to estimate the channel. So basically we have to know what inter-symbol interference is, and to ultimate goal having is ISI free transmission. Motivation of ISI. For any digital communication system, ISI is a form of distortion of the symbol or the signal in which one symbol interferes with a subsequent symbol. Here you can see when a signal is passed through a band limited channel, it will try to, or it will smear its edges to other symbols. So this region is the interference region. This region is the interference region. Mathematically, if you model it, xk is the transmitted signal, hk is the channel, and n is the noise. This is ISI, which means IS symbol is interacting with other channel gain but not its own, thus producing ISI, inter-symbol interference. So we have to compensate the interference, and also since the channel is changing, we have to adapt this equalization. That means we have to have an adaptive algorithm which should be doing the same thing, is inverting the filter. How it is different from diversity? Diversity is nothing but to mitigate the or reduce fade by reducing the depth and duration of this fade. So basically our objective by using AWGN and fading is because AWGN channel requires a very less SNR requirement for a given BER. Fading channel requires 20 to 30 dB more SNR. This is the collective diagram of the channel impulse response, where the entire modulator block, the channel and the receiver is shown, a noise is added, and this yt is the equalizer input which gives an output to the decision maker. Now what the decision maker does, it simply checks if the received signal is same that should be received or not. If not, it has an error which will adapt the equalizer. So it means that basically if there is an error with the received signal, if there is an error from the received signal with the reference symbol, it will give an error and it will adopt the equalizer filter response. So basically what we are having is, we have an equalizer which can be modeled as an FIR filter. So here is again the same thing which has been mentioned. The error signal is driving these weights W. So every time this weight update is done, so this filter impulse response is changing. So basically how an equalization works is the same thing as has been discussed in this slide. So if you model it is as an equation, xt is the transmitter symbol which is convolved in time domain with the collective impulse response and the noise. Obviously obviously you have to add the additive white Gaussian noise. You have the received symbol or the received signal which is input to the equalizer. Now what basically equalizer does is take this filter, invert it, and does the inversing of the channel impulse response. This is the classification of various equalizers. We have linear and nonlinear, but basically we would focus on these part, which says the algorithms for the equalization which can be used on any of the linear and nonlinear classification of the equalizer. Zero forcing algorithm. Zero forcing is nothing but having the channel impulse response, inverting it, and simply having the equalization impulse response. But the difference is here we have to follow the Nyquist criteria, which means that at sampling instances it should not be driven to zero, but at other instances it should be driven to zero. So it is nothing but again has an inverse filter which undoes what the channel does. So here in metric notation it is shown like this: y is equal to h plus n. Now again, if you divide the entire equation with h, you will have the intact symbol, and here the problem is lies here. Your noise will be amplified by this factor. If h tends to 0, your noise will be amplified. So here obviously you get no IC, but the noise will be amplified. In MMSE equalization, which is an added advantage from the zero forcing, which is more robust than zero forcing, what it does is it has the errors that we talked about in the previous slide. It finds the difference and it minimizes with respect to some weights. So this is the weight vector wk. Wk is the weight vector. So it minimizes with respect to wk, the error function or the cost function. These are the simple matrix definitions which are basically used or replaced here. This is the cross correlation matrix, which is nothing but the cross correlation between the input and the output, and this is the input covariance matrix, which is the input symbols are finding the covariance of the input symbols. Now basically what it does is you have the error function, you square it and you find the expected value, and you minimize this expected value. You find the weight vector, something like this. When we implement this into this equation, we find the optimal weights. Now for the sake of simulation, we have considered BPSK, and if you put this BPSK signal into AWGN and Rayleigh fitting channel, the impulse response is something like this, and the BER is shown something like this. Here clearly you can see that AWGN channel is far better than Rayleigh fitting. For a given example BER, say 10 to the minus 3, there is a huge SNR requirement for Rayleigh fitting to have the same characteristic as that of AWGN. So it is pretty clear AWGN is far better. Something has to be done for the fitting. So this is the zero forcing implementation basically. Here we have the channel matrix, which is this, and we implement Rayleigh fitting something like this by adding two Gaussian noises, and we find the meshed, we do the meshed filtering, and we do the hard decision and error counting. Basically what it does is we have the filter response, and we have to increase the number of taps, or we have to increase the number of weights in the equalization. So it is pretty clear that if you increase the number of weights, or if you increase the number of filter coefficients, performance will increase. But to what extent? To this extent. If you see, the improvement is not much. So here some kind of saturation happens. So beyond this, the number of filter coefficients will not be increased. This is the zero forcing. We go to MMSE. This is nothing but the code shows a comparison between zero forcing and MMSE. If you simulate this code, you will find the zero forcing and the MMSE plotted on the same diagram. If again with the same given BER, you see there is not much, but only maybe 1 dB or 0.5 dB better performance in MMSE than zero forcing. So why do we implement MMSE if there is only 0.5 dB better? The main advantage is zero forcing does the noise amplification, which MMSE does not. So it is a pretty much better to use MMC than 0%. We are basically statistically minimizing the error in MMC. If we go back to the slide, the performance has been shown here, and to draw in comparative analysis, we see the concept of diversity is analogous to increasing the number of tabs. What it means is if you keep on increasing the number of tabs, or if you keep on increasing the filter coefficient, you will have better performance, but to some extent. This is called the law of diminishing returns. Listener improvement with the same BER, thus implying it is not advisable to increase the number of tabs further than 7. If you see clearly here, you have 7, which is this black line. This is the best performance. If you increase the number of delay, you don't get better performance than this, or you don't get considerably better performance than this. So 0% amplifies noise, which MMC does not. Again, the trade-off is for MMC or any kind of algorithm, basically you have to adopt the filter coefficient. You have to have a step size. Now, if you have a bigger step size, your conversion will be faster. But again, if you have a bigger step size, your precision may not be that much. So there has to be some trade-off with having a step size. So this is a typical example of a channel capacity. Channel capacity is minus 1.69 dB, gives a BPSK error of something 0.122, which is shown in the graph. Also, it implies that the simulation is correct, and we cannot improve better than this. We cannot go beyond the channel capacity. So this is just for the sake of showing the simulation is in line with the theory. Is MMC always good? Probably not, because at this point, at null, maybe the 0% is too bad, but the MMC is not that much good. Probably we have to use non-linear DFEs or non-linear direct feedback equalization. Conclusion: filter weights has to be adopted periodically. As we have said earlier, we have to have a periodic update of the filter coefficient so that we can cope up with the channel. We have to minimize the mean square error, which is obviously a stochastical gradient algorithm or LMS algorithm. The channel estimation is a prime concern. As we all know, we have to have an idea, clear-cut idea of how channel behaves, and it all comes down to channel estimation and then adapting the channel and then implementing either 0% or MMC. Thank you.